which is entitled the germicidal ultraviolet light side-emitting optical fibers for inhibiting biofouling formation on reverse osmosis membrane processes. So this is the contents of my talk today. So I'm going to start my talk with a brief introduction. Water shortage and concern over anthropogenic pollution is necessarily increased reliance on impaired water supply to meet the growing water demand. Alternatively, membrane-based water treatment processes are gaining great attention due to their strong applicability and water quality management and production costs. Among them, nanofiltration and reverse osmosis membrane desalination are central to increasing the water supply for high-quality water from seawater, brackish water, groundwater, and wastewater. However, biofouling is a major contributor to increase in operational cost membrane process because it increases pressure requirements and chemical uses and decreases water fluxes. Biofouling generally occurs from biofilm formation, which are surface-bounded complex microbial aggregate encased in cell produce extracellular polymer substances that are primarily composed of polysaccharides and proteins. Numerous strategies have been explored to mitigate biofilm formation on reverse osmosis membrane, including pre-treatment to remove biodegradable organic matter and adding chemical to disinfect biofilm or modify membrane surface for anti-fouling material. However, their use in combination has not yet to eliminate the biofilm formation on membrane. Chemical cleaning using various cleaning agents are widely used to control fouling of membrane-based water treatment process. Because of protection provided by EPS metrics, biofilms have strong resistance to chemical penetration and hydraulic cleaning cycle. Bacteria reportedly produce more EPS under these kind of stressed conditions, thus requiring excessive cleaning agent to control biofouling in reverse osmosis membrane, which lead to the secondary environmental pollution. In addition, polyamide membrane inevitably degrade during chlorine-based cleaning cycle and require more frequent replacement. Therefore, there is a critical need to develop biofouling control technology that can effectively inhibit biofilm formation on reverse osmosis membrane surface. Alternatively, germicidal ultraviolet light-based disinfection process such as UV-C direct disinfection and photocatalytic disinfection using RHO is a proven non-chemical strategy. Traditionally, ultraviolet lamps use UV light generated from mercury sources. This UV mercury lamp has relatively high power for disinfect but short life expectancy. And also mercury toxicity and high maintenance cost. UV LED are emerging for disinfection application because they are mercury-free and compact and require low power and have long life expectancy. And also LED wavelengths can be selected to disinfect bacteria through different mechanisms. However, the major challenge for UV LED is their relatively low power and small irradiation area and ability to deliver light into different reactor configuration. To overcome these limitations, side-emitting optical fiber, SEOF, have been developed to deliver light to surface or create higher surface area in the process. UVA wavelengths delivered into the optical fiber coated with TiO2 nanoparticle effectively generated reactive oxidant species which can degrade organic matter and contribute to microbial inactivation. UV-C wavelengths are more effective for disinfection than UVA because of the action spectra of DNA and protein in the bacteria. Therefore, we envision that these SEOF can replace or be integrated with the membrane spacer that are used in all spiral wound of reverse osmosis membrane module to deliver sufficient UV light to the inactivated bacteria or produce reverse RS for disinfection and oxidation of soluble microbial product. So this is a material method. The fabrication step of UV-C, UVA, SEOF, disinfection, photocatalytic oxidation are illustrated in the left top figure. For UV-C side emission optical fiber, silicon nanoparticles were coated on the optical fiber surface because UV-C has a short wavelength and higher reflection rate on the optical fiber surface, thereby leading to a less uniformity of light distribution along the fiber. Therefore, silicon nanoparticles were coated on optical fiber surface to control refraction rate of optical fiber, which enable uniform side emission of UV-C. In contrast, UVA lower reflection rate on the optical fiber surface, thereby leading to a quite uniform side emission of UVA light without silicon nanoparticle. Thus, TiO2 nanoparticles were directly coated on the optical fiber surface that can generate the reactive oxygen species from UVA side emission optical fiber surface. The right bottom figure showed that two side emission optical fibers that are side emitting light when connected to a function LED, which is located inside of the membrane cell. As you can see, left top figure, light was uniformly emitted from the side emission optical fiber along their length. Thus, nanoparticle coating was effectively deliver light to the surface of side emission optical fiber. Despite applying the same current to the UV-C and UVA LEDs, the side scattered light for the UVA side emission optical fiber was about 100 microwatt per square centimeter and was higher than 10 microwatt square centimeter from the UV-C side emission optical fiber. For the 360 nanometer LED and TiO2 coated side emission optical fiber, the photocatalytic behavior was demonstrated by the oxidation of benzoic acid to para-benzoic acid. And no PHBA for non-coated optical fiber attached to the UVA LED, but the PHBA formation increased gradually over time from the TiO2 coated side emission optical fiber. This result indicates that the UVA side emission optical fiber generated the hydrogen radical to inhibit the bacterial growth. Then first, we compare the water flux and salt rejection and biofilm thickness of reverse osmosis membrane without light versus reverse osmosis membrane with UV-C versus UVA side emission optical fiber. Second, we quantify the changes in membrane surface property after exposure to UV-C and UVL light by side emission optical fiber, and we use bacterial cell count, chemical analysis of membrane filament, and transcriptomic analysis of biofilm to discuss potential mechanism for how two different wavelength side emission optical fiber influence biofilm mitigation on reverse osmosis membrane process.
Mr. Hojung, can you speed up, please?
Okay. So left figure showed that water flux salt rejection during controlled UVA radiation. So normalized flux was 3 reverse osmosis membrane decreased over time, indicating some biofouling likely occur on the reverse osmosis membrane. However, as you can see in the figure, the side emission optical fiber, which is equipped with UV-C and UVA LED, were decreased the biofilm formation. And also, these results are characteristic of biofouling membrane surface. The left top figure shows that surface zero potential reverse osmosis membrane became less negatively charged and the biofouling layer formed on the membrane. Also, UV-C side emission optical fiber resulted in the surface contact angle closer to the virgin membrane than control membrane system. UVA side emission optical fiber resulted in a surface with the lowest contact angle. This is likely indicated larger biofilm accumulation on reverse osmosis membrane equipped with UVA side emission fiber without LED. To investigate how bacteria are responding to UV-C radiation or generated hydroxyl radical by UVA, biofilm sample was subjected to the transcriptomic analysis. While the photocatalytic UVA side emission optical fiber has significantly more effect on the oxidative stress response, UV-C side-emitting optical fiber that directly deliver germicidal radiate to the membrane surface sufficiently inhibited biofouling formation, affecting the expression of quantum sensing regulation and surface attachment gene. While there is a potential for UV light to damage the polyamide reverse osmosis membrane, the previous research revealed that there is no adverse impact affecting the performance of polyamide membrane up to 12 joules per square centimeter of UV radiation, which is amount required to be irradiate UVA side-emitting optical fiber for about 3 months, assuming that no accumulation on the membrane surface. Moreover, ongoing research suggests continuous irradiation may not be required to control biofilm growth. If the UV dose is greater than bacterial growth rate, then biofilm growth was inhibited. Therefore, we are exploring duty cycling wherein LEDs are cycled on for a short period of time and then off. This lengthens the operation time to several years before accumulated dose, even approaching levels previously found to cause membrane defect to the polymer surface. So to summarize my presentation, we demonstrated the reverse osmosis membrane unit equipped with the UV side-emitting optical fiber effectively inhibited Pseudomonas aeruginosa growth on membrane surface, mitigating adverse performance decline in wall flux otherwise associated with the biofouling. And also UV-C side-emitting optical fiber resulted in more constant performance than control experiment where biofilm grows on the membrane surface. To conclude my presentation, we demonstrate the reverse osmosis membrane unit equipped with UV-C side-emitting optical fiber to inhibit the biofouling of membrane surface. And also, the generated hydroxyl radical by UVA side-emitting optical fiber promoted to accumulate extracellular polymer substances and bacterial cell on reverse osmosis membrane. While there is a potential to UV light to damage the polyamide membrane, continuous UV radiation is not required to control biofilm growth. So we are currently seeking a funding for manufacturing a spiral wound module, side-emitting optical fiber, and reverse osmosis membrane to derive the optimal operation condition of side-emitting optical fiber and evaluate techno-economic analysis. So thank you for kind attention.